This equation here is called the wave equation, and the way you solve it is similar to the heat equation if you solve it using the separation of variables as before. So because this left side is differentiating twice in x, if you simply plug this into the left side, you get k squared x double prime and then t. And I'll suppress parenthesis x here. This x double prime really means x double prime x, okay? And then on the right side, because you're differentiating twice only in t, this will become x times t double prime. And just like in the heat equation, you want to divide both sides by the constant times xt. But in heat equation, I told everyone to divide by kxt, right? However, here the constant is k squared, so we're going to divide everything by k squared xt. And let's see what happens. If you divide both sides by k squared xt, k squared xt, then here the x's cancel out, here the k squared cancel out, and the t cancels out, and what you get is x double prime over x equals to t double prime over parenthesis k squared t. And then you set that equals to negative lambda, because as the standard argument in the separation of variables goes like the left side is only dependent on x, the right side is only dependent on y, no, and t in this case, and therefore they should both be constants. And you name this constant traditionally as negative lambda. Okay, so that's what goes inside here. Let's move on. Since these differential equations are independent of each other, they can be separated. So first of all, if you have x double prime over x equals to negative lambda, if you multiply by x both sides, so that this cancels, and then you move this to the left side, you end up with x double prime plus lambda x, and that's what goes here, plus lambda times x. And this is a WebWork question where you have to put this lambda as lambda. Don't forget that b, okay? Lambda is spelled with b. All right, and then for the other one, you have t double prime over k squared times t equals to negative lambda. And this is basically same as the previous one. The only difference is there's a k squared that gets multiplied to lambda as well. So you're going to get t double prime plus lambda times k squared t. Okay. Now we solve the separated ODEs for the different cases in lambda, in each case the general solution in x is written with constants a and b, and the general solution in t is written with constants c and d. Write the functions alphabetically. Yeah, so for this WebWork, I found it a little tricky, because if you write down your functions in the wrong place, it wouldn't accept it. I hope the author for this question took some time to accept many variety of different answers, but they only accept one kind. Okay. So first of all, when lambda is 0, let's see, if you have x double prime plus 0 times x equal to 0, that simply means x double prime is 0. And then when you integrate both sides, you get x prime equals to some constant. Let's call that a. And then you integrate both sides again, and you end up with x equals to ax plus b. So this is what I originally put in, but the WebWork for this alphabetical order, see, you really have x and 1 as two solutions, right? And since numbers should appear before letters, apparently, yeah, in alphabetical order, that's the convention, okay? So it should be really a times 1 plus bx, so that's what goes in here, a plus bx. Same thing here, if you plug in lambda equal to 0, you get t double prime equal to 0, so you're going to get c plus dt. t is the variable here. And then u, because our original assumption was that u is x times t, you just simply multiply these two and you're done. Okay, now let's move on. Okay, how about this one? Here, lambda is negative alpha squared, so in this equation when we had x double prime plus lambda x equal to 0, instead of lambda you have negative alpha squared, so you get x double prime plus alpha squared, actually minus alpha squared, x equal to 0, because lambda is negative alpha squared. And this one, if you solve the characteristic equation, it will be r squared minus alpha squared equal to 0, whose solution will be r equals to plus or minus alpha. And here's the problem. Usually, if you have these two, because alpha is considered as real, the two solutions must be x equals to a times e to the alpha x plus b times e to the negative alpha x. However, these functions are not so great when you try to use it for solving partial differential equations, notably because they're not neither even nor odd. So instead of these, people come up with cosine hyperbolic of x, whose definition is basically the symmetrized version. So this is an even function obtained by taking the sum of the two functions and dividing by 2. And sine hyperbolic of x is like you take e to the alpha x minus e to the negative alpha x over 2, and that gives you an odd function. And these two are linearly independent, and you can express any function of this form into some linear combination of these two. And that's why it says use cosine hyperbolic, sine hyperbolic. So your answer should be a times cosine hyperbolic of alpha x, and then plus b times sine hyperbolic alpha of x. And for the t, it's the same story. You will see that the solutions will be of the characteristic equation will give you not alpha, but because there's a k in the equation for t, you end up with alpha k t, and d cosine hyperbolic, no, sine hyperbolic alpha k t. And there's no space between cos and h. This is one word, cosine hyperbolic. So when you put it into u, again you put a cosine hyperbolic alpha x plus b sine hyperbolic alpha x times c cosine hyperbolic alpha kt plus d sine hyperbolic alpha kt. So that's it. And for the case when lambda is alpha squared, this time the characteristic equation for x would be r squared plus alpha squared equal to 0, whose solution is r equals to plus or minus alpha I, and that gives you the general solution as x as a cosine alpha x plus b sine alpha x. And what it amounts to is that if you do the x and for the one for the t, you'll see that it's basically the case too, except that it's not the hyperbolic cosines or sines, it's the usual sines and cosines. So the answer here will be a cosine alpha x plus b sine alpha x, and c cosine alpha x, alpha kx, plus d cosine alpha kx, kt, sorry, this t. Okay, and then finally you take the product of them, and that's the solution for this entire question. Okay, let's write them down. kt plus d times sine alpha kt, and that's it.